Hello, Ed Wicklein with Corollo Engineers. I'm here today to talk a bit more about the technical guidance manual on computational fluid dynamics modeling of chlorine contact basins. This is the final installment of our modules. Today we're going to be talking about data processing and reporting. Hopefully you've had a chance to review all of the prior modules. So this is a sample problem we've been talking about. It's Appendix B in the guidance document. It's a small, typical chlorine contact tank, and we're going to be picking it up at post-processing. We've run the model, and we've output our data here for a number of time steps throughout the simulation, and written output at the outlet to track how the tracer is exiting the system. So we open the data file in a processing visualization software. CFD models, of course, give us a lot of information. It's best displayed graphically. And so in the guidance document, we have a couple sample images. This would be a section view at the center line of the inlet and outlet with the velocity contoured between 0 and 1 foot per second. So anything that's greater than 1 foot per second would also appear as red. We've got some stream traces showing the flow path. We've got another image here higher in the water column looking at the velocity again. We don't have any stream traces in this image, as they would be harder to visualize below the level of this slice. Then we've got some section views through the domain, so we can see the inlet jet here starts to expand and dissipate and creates a recirculation cell. As we move down the passes, everything starts to become more similar as it goes through each bend in the wake region. So within the visualization software, I've got the model open here. We can make it translucent, edges, make a few adjustments here so we can see what's going on inside a little bit better. Turn off some surfaces we don't necessarily need. And we can rotate this and look at it in different ways. So within the model, we can turn on the slices as we saw before and set these up to be representative of different areas that we might be interested in. We can look at different contour variables that are loaded within the model, and then we can adjust the scale to see how to visualize or just better visualize things. So initially we had a scale of 0 to 1 foot per second. And here we are at the exact mid depth. And so it's a little bit different than what we saw before. The inlet here, we can change our scale if we want to look at different features, perhaps double it. The velocity is very low in most of the cells, with the exception of this first one where the inlet jet's characterizing the flow. We can look at some other section views. We can look at the center line of the inlet. Or just off the center line and turn off the slice, see how the jet enters. It starts to rise. There's a recirculation. If we want to add stream traces to see how flow's moving through this, we can. They're seated along the plane, and so we'll see this recirculation and then flow travels down the domain. We're also able to look at or develop animations. So we'll switch what we're looking at here and lower this to the center line of the pipe. And so here's the velocity at the center line of the pipe. We'll switch our contour variable to our tracer. In this case, it's scaled from a fraction of 0 to 1. As you recall, we set the inlet tracer fraction as 1, so 0 would mean there's no tracer. That's the water that's in the tank. Anything that's red is, or presently yellow. They changed the contour scale in the software, so still getting used to that. So anything that's tracer is red, so we're starting with the tracer right at the end of the domain. And we're able to create an animation, step through time, see how the tracer moves through the tank and develops. We can step back at any of these time steps where we've written out our data. And those are some of the figures that you may see developed for the reports. So again, here's the tracer at 2 time steps. Finally, we need to generate our tracer curve. So as the model has been running, we've written an output file. Here, in this case, it was M3 9 pass out. And so we'll go to that file and open it. Here. And so you can see it's a text file listing information, the time step, the flow time, the tracer, total volume of tracer in the domain, and the tracer coming out. This text file, typically we read into Excel for processing. And so we would have it here. Typically, I import it and then copy it over and couple it with the normalized time to generate the plot of the tracer curve. So that way we can easily compare our different flow rates, 4.5 and 2.5 MGD in this case. And so there's not a lot of difference between the two. If we zoom in on the scale, we can probably see a little bit more difference. The T10 value, it doesn't change a lot. During the mid-range, there's some change, and again, they start to converge as we continue down. And so the tracers here, the tracers here, converted to a volume, and using a lookup table, we're able to look up when we reach a factor of 0.1 or the T10. So in this case, at our peak flow, we're at 0.844 for our T10, and at the 50 percentile flow of 2.5 MGD, we're at 0.84. So how did this compare to our initial estimate based on the length to width ratio? The model predicted to be 0.87 approximately. So the CFD model is a little bit more conservative than the table. Of course, the classic table is developed from a bunch of models, and so it doesn't account for everything, but in general, based on our model coming in within just a couple percentage of this, we would say that we have a fairly accurate model. We're within the range of expected values, and so we would round this down and probably recommend a factor of 0.8 for this basin. Following the data processing, prepare a report. There's a sample in Appendix B as noted, and the report's going to be stamped by a Colorado engineer to verify that it meets the standard of care for professional engineering. Table of contents walks through the information that we'd like to see presented, and got introduction section, review the model, our estimated tracer curve, review of the CFD modeling approach for this case, our mesh sensitivity analysis, a documentation of convergence, demonstrating that we do have a mesh independent solution, image of the final mesh so we can see that it appears to be a good quality mesh, discussion of model results, figures presentation, and finally our tracer curve with our recommendation, rounded down to 0.08. Following that, the modeler should also put together the model checklist to help the reviewers. And I did not have that file open, but if you give me just a moment, I will pull it up. So the accompanying filled out guidance document or documentation for the report would be here. Who did the modeling? That would be me in this case, Colorado licensed engineer. And so go through the checklist and make sure that these things are here. Yes, it's all included. Then the reviewer can go in and verify that indeed they can find it. When the project was completed, project cost estimate, the flow rates modeled, room for discussion, documentation of where things are in the report to help the reviewer find it, some of the key values. And it's generally pretty self-explanatory, and then figures that need to be included. If there's any additional information you want to provide, it can be provided here to help the reviewer with the document. And with that, we've gone through the complete guidance document, how to set up a CFD model, how to process the data, how it should be reported and documented for CDPHE. If you have any questions, feel free to reach out to me. My email is here, or CDPHE. We will have one final session that will run live with Q&A, and you'll be able to find more information there. Thank you for watching all of these videos. Have a great day.